Example 6 wants us to find the indefinite integral of 1 over x squared minus a squared dx, where a is some constant that's not equal to 0. Before we do anything, I'm going to factor the denominator because that is a difference of squares. So it's going to factor into x minus a times x plus a dx. And so now we can start to use partial fraction decomposition. I'm going to take my integrand, and I want to rewrite this as some fraction with the denominator of x minus a and another fraction that has a denominator of x plus a. And I still don't know what the numerators are, so I'm going to name one capital A and another one capital B. Don't get your lowercase and your capital A mixed up. So I'm going to go ahead and clear my fractions by multiplying by the least common multiple of all of the denominators. And my new resulting equation would be 1 equals a times x plus a plus capital B times x minus a. Once again, I can use the technique of plugging in strategic x values. So one of them is lowercase a. I can do that. That will give me 1 equals capital A times a plus b times a minus a. So that's going to go to 0. And remember, we're trying to solve for capital A. So I get 1 equals capital A times 2a. I'm going to divide both sides by 2a, and that's going to give me capital A is equal to 1 over 2 times lowercase a. Now I can also let x equal negative a. And then I get 1 equals capital A times negative a plus a. That's going to go to 0. And then plus b times negative a minus a. So now we get 1 equals b times negative 2 times lowercase a. And then if I solve this for b, I get b equals negative 1 over 2a. Okay, so we found capital A and capital B. I'm going to replace those. So I have 1 over 2a, and then minus 1 over 2a, like that. So I want to take the integral of this thing, and so I can integrate this. Now I'm going to go ahead and split that up into 2 separate integrals, and I'm going to also factor out the numerators. Remember, lowercase a is a constant, so I can do this. So these both have 1 over 2a, and let's solve the first integral. That's going to be the natural log of the absolute value of x minus a, then minus the natural log of the absolute value of x plus a, and then plus our constant of integration. Now, because we have a natural log minus a natural log, I can actually use one of the logarithm laws to combine that into a single logarithm if we wanted to. So this is equivalent to 1 over 2a times the natural log of the absolute value of x minus a over x plus a, and then plus c. So here is our final answer for this one. So here in this purple box, we have that it's just showing that the indefinite integral of 1 over x squared plus a squared dx is equal to 1 over a times arctangent or tangent inverse of x over a plus c. Now, you can actually show or prove this statement by using trigonometric substitution. I will leave that to you if that's something that you're interested in doing. Let's move on. What if the denominator is an irreducible quadratic of the form x squared plus px plus q? That is, it cannot be factored or does not have any real roots. In this case, suppose that x squared plus px plus q all to the nth power is the highest power of this factor that divides the denominator. Then, to this factor, assign the sum of the n partial fractions. So this is what it would look like. You would have to make that your denominator, and create n of these fractions until you hit the highest power here. So for example, we have x minus 1 squared there. I will need 2 fractions just for that. And then here I have an irreducible quadratic. And just as a quick reminder, x squared plus 1, if I were to graph that, that would be a quadratic that's shifted up 1 unit. And that's not crossing the x-axis, so it has no real roots and therefore is an irreducible quadratic. What does that mean in terms of when we're trying to break this up into multiple fractions? So I have negative 2x plus 4 over x squared plus 1 times x minus 1 quantity squared. And we're going to need 3 different fractions. One with a denominator of x squared plus 1. Now, because in this fraction my denominator is an irreducible quadratic, I need my numerator to be 1 degree less than that. And 1 degree less than that is going to be a linear term. And that's why here in these numerators we have bx plus c. So here I'm going to call this ax plus b. My next fraction is going to have a denominator of x minus 1, and I'm going to use the next capital letter that's available, which is c, and then my next fraction, I need x minus 1 quantity squared, and then I'm going to give that a d, as that's the next capital letter. So again, here I'm going to use the method of clearing fractions. So I'm going to multiply every fraction in this equation by the least common multiple of all of the denominators. And I'm going to write out my resulting equation. Okay, so I went ahead and I multiplied my least common multiple through, and this is the resulting equation that we get. From here, what I'm going to do is I'm going to plug in a special x value. I'm going to let x equal 1. Now, this is a scenario where this method kind of works, and what I mean by that is here, this is an irreducible quadratic, which means that there's no value for x that I could plug in that's going to make disappear. So we're able to use this method a little bit, but not for the entirety of this equation. So on my left-hand side, I'd have negative 2 times 1 plus 4 is equal to, the first 2 terms are going to disappear, and so the d term is what we're going to have left over because the other things are going to become 0. So I have d times 1 squared plus 1, and if I simplify this, the left-hand side is going to become 2, and then on the right-hand side we'll get 2d, which will imply that d is equal to 1. So let's go ahead and plug that in here. And if I multiply 1 times x squared plus 1, that's just going to give me x squared plus 1. So we found that d is equal to 1, so I replace that there. Now what I'm going to do is I'm going to move these terms over to the other side. So I'm going to subtract x squared on both sides, and I'm going to subtract 1 on both sides. And if I do that, let's see what happens. Alright, so this is what we get when we simplify by subtracting x squared and subtracting 1 on both sides. I'm also on the left-hand side going to factor out a negative sign, and if I do that, here is what I get. And then inside my parentheses, I'm going to factor that as well. So that's going to give me negative x plus 3, and then x minus 1. So I'm going to copy that up here. Why is that helpful? Well, what I'm going to do now is, my goal is to solve for capital A, capital B, and capital C. And so what I'm going to do at this stage is I'm going to divide x minus 1 on both sides. And what that's going to do is this x minus 1 will cancel with this x minus 1, and then here that'll leave a single 1 in the numerator there, and then these will divide out. So we had negative quantity x plus 3 is equal to, okay, so here's our resulting equation. I'm going to distribute this negative sign here, and then I can FOIL, so I get ax squared minus ax plus bx minus b plus cx squared plus c. Let's go ahead and rearrange our terms. So I have ax squared plus cx squared plus, I guess it's minus ax plus bx, and then minus b plus c. Now let's factor out any of the x terms. And on the left-hand side, we have negative x minus 3. Now notice here we have an x squared term, and we don't have one on the left-hand side. So if it helps you, you could put 0x squared. And so now if we're comparing coefficients, I have that my coefficient of x squared on the right-hand side is equal to 0. Let's use some different colors. My linear term, I have my coefficient is negative a plus b. That's equivalent to negative 1. And if you want, you could put a negative 1 there. And then my constant term, I have negative b plus c. And then on this side, my constant term is negative 3. So let's go ahead and set up our system of equations now. I have a plus c is equal to 0. I have negative a plus b is equal to negative 1. And then my last one is negative b plus c is equal to negative 3. How do I go about solving this system of equations? Well, one thing you might notice is if I were to add all three equations together, so if I'm just putting a plus sign here, if I add a plus negative a plus 0, that's going to give me 0. If I add 0 plus b plus negative b, that's going to give me 0. If I add c plus c, that's going to give me 2c. And then 0 plus negative 1 plus negative 3, that's going to equal negative 4. That worked out really nicely, and that technique unfortunately is not always going to work, but they kind of lined up, or the stars aligned, if you will. So I have 2c is equal to negative 4. If I divide both sides by 2, I get c is equal to negative 2. And in my first equation, if I do a plus negative 2 is equal to 0, that implies that a is equal to 2. And then we can, let's do the second equation. So I have negative 2 from my a value plus b is equal to negative 1. If I add 2 to both sides, I get b is equal to 1. And then from earlier, we had d was equal to 1. So let's go ahead and plug these all back into our fractions that we had. So I went ahead and split up my original fraction into these three fractions. And now we have to figure out, how do we integrate this thing? So why don't we break this up into multiple integrals first? So this is going to equal the integral of 2x plus 1 over x squared plus 1 dx minus 2 times the integral of 1 over x minus 1 dx plus the integral of 1 over x minus 1 squared dx. So I think the middle and the last one are not too bad to deal with here. So let's deal with those. So this middle integral, that should come out to be, if I ignore the constant, it's going to be the natural log of the absolute value of x minus 1. Here, for this one, let's use u substitution. So that's going to turn into the integral of 1 over u squared du, which if you think about that as u to the negative 2 power, that's negative 1 over u plus c, and u was x minus 1. So now we just have to deal with this first integral here, and it might not be immediately obvious, but this is a trick that you could do to deal with this. You could actually break that up into two different integrals. I'm going to break it up into two fractions. So the numerator I can break up into 2x and then 1, so I get this. Do you recognize these, or how to solve them? This one is equal to arctangent of x. We actually saw that in the purple box earlier. And then this one, we can use u substitution. I'm going to let u equal x squared plus 1. Then du would equal 2x dx. So my integral would become 1 over u du. And then that's going to become the natural log of the absolute value of u plus c. Let's replace u with x squared plus 1. On a couple of these I forgot plus c, but I mean all of the constants we can kind of combine into a single constant. It's just an arbitrary constant. So let's go back and kind of give our final answer. So we have that our original integral is equal to the natural log of the absolute value of x squared plus 1 plus arctangent of x minus, don't forget this constant here, so minus 2 times the natural log of the absolute value of x minus 1, and then minus 1 over x minus 1 plus c. And here is our final answer.